In the past couple of segments, we've talked about both supervised and unsupervised learning. From here on in, I'm going to focus on unsupervised learning, and in particular on clustering. Not because clustering is more important than supervised learning, but because it's a bit easier to show you how to do it. Of course, I don't want to give you the wrong impression that it's unimportant. We're just looking at it because it's easy. In fact, it's enormously important. As you'll recall, the idea of clustering was to find an intrinsic grouping in a set of unlabeled examples. We're looking for some latent structure in a set of examples. It's of great practical utility. It's used in marketing, biology, insurance, medicine, and lots of other things. For example, if we think about marketing. For those of you who don't know what marketing is, think about it as the art of getting people to buy things they don't actually need. So for example, Walmart is masterful at using machine learning to figure out where to arrange things in the store, what objects should be near what other objects, so that people will make impulse buys. Netflix has very sophisticated algorithms for deciding which movies are similar to each other, which viewers are similar to each other, and how to match people with movies they might want to pay for. Amazon does that much more broadly, originally with just books, but now almost anything you can buy online, Amazon is figuring out what are the clusters of things that would be attractive to you. In the world of science and medicine, we also see a lot of clustering. This depicts a clustering of people. Each color is a different cluster, and it's intended to show how people might react to particular therapies, which people might react well or badly to the same therapy, for example. Here we see a depiction of the use of hierarchical clustering, something we will look at doing to relate genes to one another. In the world of insurance, clustering is used to avoid fraud, for example, medical fraud. Find out which claims are like which other claims, which claims are unusual and therefore potentially fraudulent. And as depicted here, it's used to separate really very bad drivers from other drivers so that insurance rates can be set appropriately. Well, what makes a clustering good, or conversely not so good? There's no general answer to that, since it depends entirely upon the application. So let's look at an illustrative example here. We've seen something similar to this before, where we've taken people and plotted height on the y-axis, weight on the x-axis, and I've added a third dimension here, color, to represent political affiliation. In the United States, blue is usually used to indicate a Democrat and red to indicate a Republican. So what makes a clustering good? Well, suppose we're trying to figure out who might be a good basketball player. Well, probably these are the right two clusters, the tall people and the not so tall people. On the other hand, if we're looking for sumo wrestlers, maybe we want the light people and the heavy people in clusters together. And if we're looking for potential political candidates, we might well want to separate the Democrats from the Republicans. Again, the moral is, before you can decide how to cluster, you need to know why you're clustering. Once you know why, what you need to do is find an objective function, because after all, we're dealing with an optimization problem. Like all machine learning, we're either minimizing or maximizing some objective function. In clustering, there are at least two things to consider. We want low intra-cluster dissimilarity. By that I mean if points are within the same cluster, we want them to look like each other. And we want high inter-cluster dissimilarity. By that I mean if points are in different clusters, we want them to look different from each other. We can look at this a little bit more rigorously, and I'm sure some of you have been just dying to see an equation. Let's look at the variance within a single cluster to get intra-cluster dissimilarity. So C is one cluster, V for variance. How are we going to measure it? Well, the way we've measured variance before, by looking at the mean square difference. We'll find some way to compute the average value of a point in the cluster. So if our objective function is dealing with weight, it would be the average weight of the points in the cluster. We'll subtract from that the value for a single point, the weight of a single person, and square it, and then sum it over all of the points in the cluster. That will give us the variance within a single cluster. If we then want to look at a set of clusters, we can look at the badness of the set of clusters, the dissimilarity there, by just summing the variance over each cluster in the set. Are we done? Is that all we need to do? If we can find and minimize the badness of a set of clusters, are we done? Well, not really. Suppose, for example, each example is in its own cluster. If I have 1,000,000 points, I'll have 1,000,000 clusters. What's the badness of that set of 1,000,000 clusters? It's 0, because there's no variance in any one of them. Well, that's not very interesting. I've got a trivial clustering where each cluster is very coherent. That's the word we use to talk about it. On the other hand, I haven't done anything useful. Well, what should we do? Let's think back to optimization. What do we need? Well, we need a constraint. Lots of possible constraints. For example, we might pick a distance d and say that's the maximum distance allowed between clusters. That would probably prevent us from putting every point in its own cluster. Or more simply, we might just say you can only have 5 clusters, some number of clusters, and that will again avoid a trivial solution. The problem, this is a great and classic formulation of optimization. We have an objective function and a constraint, but like many optimization problems, it's computationally very nasty, typically, in fact, intractable. What do? What we usually do, we find some greedy approximation. And in the next few segments, we'll look at 2 such approximations, k-means clustering and hierarchical clustering.